So suppose you want to find the distance to a star. So how do you do that? That's not very easy to do. It's not like you can just fly a spacecraft there and look at the odometer. We already said earlier this semester that stars are so far away that the fastest spacecraft leaving the solar system that was launched way back in the 1970s is only just now reaching interstellar space, and that spacecraft is not headed towards the nearest star, but if it were, it would take about 75,000 years to reach there. And so clearly, actually going there is not an easy way of doing it. So how do you measure the distances? And that turns out to be something that goes back for a very long time. People have been wondering about that. They started really getting to the science of this with Giordano Bruno, who in 1600 looked in the sky and said, well, if Copernicus is right, and if Copernicus is a famous astronomer who said that the Earth goes around the sun, then if Copernicus is right, then if you got stars that are out there, as Earth moves around the sun, our vantage point changes, and so it would look like the stars are in slightly different angles in the sky once Earth is moving. Well, no matter how good of an observations they made at that time, this is before the invention of the telescope, they could not measure that tiny shift in the sky. And so he made an argument, therefore, that the farther away something is, the smaller that shift is. And so since that shift could not be measured, the stars must be exceedingly far away. Well, if they are that far away, then he reasoned that meant they had to be pretty bright to be visible from Earth. And so he said if they're so far away that you don't see any motion at all, then they must be nearly as bright as the sun. So he actually reasoned they must be suns. And he even went one step further to suggest maybe they had planets around them. That was considered kind of heretical thought in those days. And so he kind of got in trouble and eventually burned at the stake. But the basic idea that he had was really not that far off. Stars, the sun is a star, so the stars can be thought of as kind of like suns. And it turns out to be a lot more complicated than that, but that's kind of what we'll be getting into this semester. First step is measuring the distance. When we're talking about measuring distances to stars, they're so far away, you have to think about even light takes a long time to get from the star to us. Light travels 186,000 miles every second. That's about 300,000 kilometers a second. So light is enormously fast. And so even so, the stars are so far away that it takes years for light to reach us. So we have a unit of distance that we call a light year. Light year is the distance that light travels in a year. It's not a unit of time. Light is not, time. Light year is not time. Light year is a distance. So we would say that stars, are like 12 light years away. That means it would take light 12 years to reach us. A light year is about 9.5 trillion kilometers. That's almost 6 trillion miles. And that's one light year. Now, the problem is, how do you measure that? And what we do is we triangulate on the stars. So if we have a star that's out here in space, if we look from Earth at the star, it looks like it's sitting in front of some really distant stars there. And then 6 months later, Earth is in a different spot, and so it looks like the star has shifted position a little bit. Okay, if the star is farther away, that shift is less than if the star is close. And so if we can triangulate on it, if we can measure that angle is called parallax. And we know how far Earth is from the sun, then this is a right triangle, so we can triangulate. We can actually use the relationships, trigonometry, to figure out that distance, the distance right there that the star is from the sun. Okay. Now, that's the idea of parallax. Your book uses the symbol P for parallax. Most other books use the symbol pi for parallax, which is like a Greek P, okay, because we use P for several other things in other equations. So I go back and forth between the two. So here's a kind of example right here of a star, okay, and you see where it is in the sky, and it looks like, you know, from our vantage point right here, it looks like the star is there. From the vantage point over here, it looks like the star is there. So it shifted a little bit in the sky. It shifted from, you know, there to there, okay? And so if you can measure the magnitude of that shift, then you ought to be able to knowing that distance, the distance from the Earth to the Sun, calculate the distance of the star. Okay. Now, the problem is measuring that parallax is really hard. The parallax is tiny. The closest star to us has a parallax that is about 1/4000th, or 4,000 times smaller than 1 degree. So that's amazingly tiny. So tiny that the very first parallax was not measured until 1838 by Frederick Bessel. And so he measured the first parallax, and that's from a relatively near star called 61 Cygni. By 1900, only about 6 stars have had their parallax measured. So this was a very difficult, very labor-intensive process. Most stars were too far away to measure any parallax. So to find distance, we define a unit of distance called a parsec. Parsec stands for parallax second. And what we do is we take the parallax measurement and divide by the parallax to get the distance in parsecs. So how does this work? Well, the distance is 1 divided by the parallax. So if the parallax is 0.1 arcseconds, the distance is 1 divided by 0.1, so that is 10 parsecs. If the parallax is 0.02 arcseconds, then the distance is 1 divided by 0.02, and so that comes out to be 50 parsecs. So this is how you do it. You just take 1 divided by the parallax, and the distance comes out in parsecs. Okay, you don't even have to like do the divide. If you buy a scientific calculator, there's usually a button that does 1/, so you just enter the number, the 0.02, and hit the 1/, button, and spits out the answers. That actually saves your fingers pressing buttons if you would like to do that. So here we have a measure. So what is this parsec thing that we're talking about? It stands for parallax second. Your book says that a parsec is the distance at which 1 AU subtends one angle, or an angle of 1 arcsecond. So what does that mean? It means if you were 1 parsec away, the distance between the Earth and the Sun, which is 1 AU, would look like 1 arcsecond. Remember, an arcsecond is, so an arcsecond is 1 degree divided by 3,600. So it's a 3600th of a degree. It's a very tiny little angle. And so this turns out to be how we measure. Now, why do we do such a weird thing? Well, that's because we used to not know what an AU was. Measuring the distance of the Earth and the Sun was also very difficult, and so the other extreme is if Earth is there and we don't know how far that is, if we know that that's an arc second, that means we can figure out that the distance to that star is going to be 1 parsec. So this is why we do this, and since we measure the parallax in arc seconds, it actually makes this a super easy calculation to find distance. You just take 1 divided by, or 1 over, the parallax angle. And then there's your distance in parsecs. You don't have to do any other calculations. Okay, so that's basically how we're going to do this. We measure, we measure the parallax of a star. We measure the parallax of a star, and we know what an AU is now, and so just 1 divided by parallax gives the distance in arc seconds. We now know that a parsec is going to be 3.086 times 10 to the 13 kilometers. That's roughly 19 trillion miles. That means a parsec is 3.26 light years. Now here's the interesting thing. The closest star to us is closer to about 4 1/3 light years. So that means the closest star is more than a parsec away from us. And so that's going to be an interesting sort of thing. In Star Wars, the protagonist Han Solo, makes a very claim that he makes the Kessel Run in so many parsecs. Well, parsec is a unit of distance, so how does he actually make the run in a shorter distance than other people? And so that was always a big question, and Star Wars aficionados, spent years trying to rationalize that as to how he could possibly do that. Okay. If the Voyager 1 spacecraft were going to the nearest star, it would take 75,000 years to get there. And so that, again, this gives an idea as to how big space is. Parallax measurements are very difficult to make, and you can make them from the ground, but a number of years ago, the European Space Agency in the 1990s launched something called the Hipparcos satellite. And the Hipparcos satellite stands for High Precision Parallax Collecting Satellite. And so it collected a whole bunch of parallax measurements that were way better than any that came before. Currently, we're working on another European spacecraft, the Gaia Spacecraft, which for about 6 years was collecting incredibly precise measurements down to 7 micro arc seconds. So 7 micro arc seconds is 0.00007 arc seconds. So that's an amazingly tiny number. And so what that means is that this satellite was able to collect distances or measure distances halfway across the galaxy. Okay, the final data release is going to come out in 2022. They've collected the data, they're processing the data, analyzing the data, make sure there's no noise in the data, and when they release it, then we'll be able to calculate with incredible precision star distances, way better than any that came before.